chapter 17 in my textbook, which is chapter 19 in Brown, is for exam 6. And this will be our next to the last exam. We have one more exam after this. And let's see. I think I've already mentioned it before, but there's no final. So when we do exam, that's right, exam 6. I said that, didn't I? Yeah. So exam 7 will be the last exam with no final. Okay, so let's get into thermodynamics. In my textbook, it's known as spontaneity, entropy, and free energy. But that's a long way of saying chemical thermodynamics. So we have a division in chemistry between what happens, how to describe the reaction in terms of beginning and ending. And that is thermodynamics. We also have a branch of chemistry that describes chemical reactions as what's going on a time scale during the reaction. That's kinetics. Thermodynamics is only concerned with what is the where does it start? Where does it end? It's not concerned with how, well, overall, it's not concerned with how it gets there, but we necessarily have to include a discussion of how it gets there in order to make sense of the before and the after. Okay. So when we talk about kinetics, we're describing rates of reaction and pathways, right? Because, for instance, catalysts make a reaction go faster. And they do that because they use a different pathway. And the pathway gets you there quicker. It gets you there with less energy required for activation. So that's kinetics. Thermodynamics focuses on whether or not a reaction will actually occur. In other words, we call that spontaneous. A reaction that is spontaneous occurs without any outside intervention. And when we say that, we also have to qualify our statement with what direction is the reaction going. If we write a reaction like this, we're saying that we're trying to describe it in terms of reactants to products. So this is the direction of the reaction. Is that direction spontaneous? Does it go without any outside intervention? Whereas if it's not spontaneous, then what if we flip it around, right? And make this the reactants and that the products? Then it would be spontaneous. Okay. So when we're looking at a diagram where we have progress of the reaction on the x-axis and energy input or any energy conditions on the y-axis, we find that in an exothermic reaction, the reactants have more energy than the products. And this is the area of thermodynamics, before and after. Whereas this part that includes activation energy and reaction rates and pathway, that's kinetics. Okay? And another way of saying that is the kinetics is always concerned with the path of the reaction. How does it get there? And thermodynamics is only concerned with the state. What is its state before? What is its state after? As I mentioned earlier, thermodynamics allows us to predict the direction of the reaction. So if we want it to go this way, but the conclusion of thermodynamics is that it's not spontaneous in that direction, then we would have to flip it around to get it to be spontaneous from left to right. It says nothing about the speed of the reaction. So the example I like to use is diamond. Diamond is a very hard mineral, and it's an allotrope of carbon. It's pure carbon for the most part. And we think of it as being eternal, right? Carbon in the form of diamond will last forever. Well, in thermodynamic terms, diamond is unstable. In other words, in an oxidizing atmosphere, where like just a diamond on your ring in the atmosphere, it is spontaneously changing. It is oxidizing from pure carbon to carbon dioxide. That's thermodynamically speaking. So the spontaneous reaction is for the carbon not to be permanent. But when we look at it in terms of kinetics, the outcome where the carbon changes to carbon dioxide, the kinetics is very, very, very slow. So it might be thermodynamically favorable to degrade your diamond ring, but it's going to take a very long time to get there, like millions of years. And so it's important to understand the difference between the two. All right. So let's look at this example. We have 2.4 moles of gas in a 4-liter bulb at a constant temperature of 32 degrees. So we have a 4-liter bulb like this. That's 4 liters. And we have 2.4 moles of gas inside. And the temperature is 32 degrees. Okay. It's connected to, by a valve, it's connected to another bulb, but this bulb is 20 liters. And this bulb is a vacuum. Okay? And we assume that the temperature is constant. Before we do anything, after we do anything, we make sure the temperature is constant. So we can't claim that the temperature has any influence on the process when we make a change. So what should happen to the gas when you open the valve? So we're going to open this valve. Right? What happens? Right? Intuitively, we know that the gas is going to go, and it's going to end up in that evacuated flask in such a way that the pressure is equalized throughout. Right? The gas spreads to fill this space. Okay? We know that's going to happen. Why does it happen? Right? What's the driving force for moving that gas into that other cylinder? Right? We can't explain it in terms of energy changes because the temperature is the same on both sides. So we need another way to explain it. I think this slide was inserted just to remind you of the symbols that we use. Remember, last semester we talked about thermochemistry. And there we were only concerned with how do we measure heat transfers in a process, right? We had our calorimeters and we did some various experiments in the lab, and we were able to judge what is the energy that's released or consumed during a reaction. So remember that Q stands for, little q stands for heat, right? And that's in terms of joules, so much heat. Work is just like the physical term work is a force through a distance, right? So work equals, if you apply a force and it's pushing against something and it moves a distance, that's work. So our example in chemical terms, we use an expanding gas. So if we had a cylinder and a piston in it, and there was a constant force here, and the piston moved up, right? We expand the gas, then work is being done on the environment, on the surroundings. Whereas if the force compresses the gas, work is being done on the system. Okay, it's just reminders. We describe the enthalpy of a reaction in terms of, well, enthalpy is more of a potential of energy production. Let's see. Yep, okay. And delta E is the internal energy. That is everything. Kinetic energy, potential energy of any kind. It's supposed to account for all the energy that's in a system. All right. Well, I just erased my diagram. So in that diagram, can we calculate these values? Enthalpy, internal energy, heat, and work for the process we described. Since there's no change in temperature, then there's been no change in Q. There's no transfer of heat. Okay, so Q is 0 for that process. Since the gas is not expanding against a force, it's not pushing up against a force, there's no work that's been done. Okay? Internal energy. There's no change in kinetic energy. There's no change in potential energy. The delta E is also 0. And since delta H, or enthalpy, incorporates this 0, and there's been no change, well, there's been a change in volume, but the pressure, let's see, that's not a good example. The volume changed, and the pressure changed. Let me see how I explain that. I would just say an all or 0. So we know that the internal energy did not change. How about the enthalpy? Well, remember, if pressure is constant, then the Q and the enthalpy are the same. If pressure doesn't change, then these two are equal. So the end result is there's been no change in any one of these. We cannot explain the movement of that gas in terms of any of these. We have to look for another explanation. And that's what chemists were doing in the neighborhood of, oh, here's the explanation. Whenever the temperature is constant, delta H and delta E are always 0. There was no temperature change at all. So all of them are 0. Working against 0 pressure, in other words, it's evacuated. So there's no work that's being done either. That's 0. And since delta E is Q plus W, it's hard to see that one. Let's see. Delta E equals Q plus W. That was from an earlier chapter. And Q and W are both 0. Delta E has to be 0. Okay. So what is the driving force behind this process? Because we know the gas is going to move into that vacuum. And it's not going to move just because it feels good, right? It moves for a physical reason. What is the driving force? We need a new definition, something new to explain why the gas moves. And that's the term S, which is equal to entropy. Entropy is difficult to understand for most people, instructors included. There are ways that we can sort of get a handle on what we believe entropy to be, and in many cases, it's a fairly accurate understanding. But to fully describe entropy, we need to invoke statistics. Entropy was first introduced around the end of the Civil War by Rudolf Clausius. Of course, Clausius wasn't in the United States, so he didn't have to deal with the war. He was what was he? Clausius? I think he was German. So what do we mean by entropy? Let's see. That keeps chopping off the bottom. We're just going to have to live with it for now. Went the wrong direction, I think. Yeah, I did go the wrong direction. Here we go. There's Rudolf Clausius. Okay. So this is a representation of an expansion, a gas expanding into a vacuum. We have a closed valve, an evacuated cylinder, and then when we open it up, the point of this slide is to illustrate the differences between the two. Notice that over here, the molecules, and there's the same number of molecules on this one as there are in this one. The difference between the two is that these molecules are occupying a larger volume. We're putting molecules into a larger space. And that, another word for that is randomness. If you get randomness in a process, if you increase the randomness, then you increase the entropy, and that's a driving force for this process. That's an increased entropy. So behind any spontaneous process, the entropy must increase. So this value must get bigger in order for the process to be spontaneous. Now, this can be confined to remember when we talked about system, right? System is this is surroundings. Right? We can also isolate both of them, right, from the entire universe. So we can talk about entropy in terms of what is it for the whole universe, right, in general terms, but it's more useful to isolate the system and the surroundings so that we can talk about entropy for the surroundings, entropy for the system. So one way to look at it is we change entropy from before the process to after the process. That's why it's often represented as a delta S, a change in entropy, which implies that you've got entropy before, now you have a different entropy afterwards. So if the change in entropy is positive, that's spontaneous. We actually increase the disorder here. You increase the disorder, delta S is positive. You decrease the disorder, it's negative. Okay, and that's possible. You can decrease the order. All you have to do is compress the gas into a smaller volume, and you've decreased the entropy. Now, this statement is true. When we think of entropy in terms of disorder, we have grossly oversimplified, but we got to start someplace. It's useful as our introductory point. Okay. A better understanding of entropy is in terms of the probability of all of these molecules being in a certain space. So we think of it in terms of the number of arrangements. How many possible arrangements of the molecules are there? Right? There are a lot, right? Because we know that 1 mole is a big number. And in any given state, we look at the number of possible arrangements of the molecules. So what we'll do is we'll simplify that. Maybe only have 4 molecules and see how that arrangement in the system can be justified. As a general rule, nature spontaneously proceeds to the states that have higher probabilities of existing. Right? If it's more probable, and we just said that entropy must be positive for the process to be spontaneous, that means it must proceed so that you have higher probabilities of these various states existing. So I need to define what I mean by state also. So here's an example. And we speak of each one of these as a microstate, right? Because there's so many of them and they're not visible usually. But suppose we have 4 molecules, A, B, C, and D. They have their individual identities. What are the possible states? Where can they be between these 2 flasks, these 2 bulbs connected? Well, one probability is they could all be in one side, right? How many possible ways can you arrange all 4 of them in one side? They can either be in that state on the left side, or they can be this state on the right side. Those are the only possibilities, to have all of them on one side. How about one of them on one side and one on the other? Well, you can put an A over here, or a B, or a C, or a D, and the rest of them are on the other side. So in that case, you have 4 possible states, where you have 3 on this side and 1 on that side. And you also have 4 possible states where you have 1 on the left and 3 on the right. Okay, so you see, we're proposing more microstates for this than for that, or for this than for that. So this is the more likely outcome so far. But what if we put 2 on either side? Right? You can have an ABCD or an ACBD. All these combinations give you 6 possible outcomes with these 4 molecules. So the most probable state is going to be this one, where you have 2 on this side and 2 on that side. You have more possible microstates in this situation than you do the others. This is the way it's going to go. where you have with equal size and equal numbers of molecules, 2 on the one side and 2 on the other. So this is the most probable one. This is the delta S would be greatest for this one. Okay, so let's look at entropy in terms of position. Right? What are the possible positions for the molecules in a substance? And let's confine our argument for the time being to changes of state. So we have this pure substance that's a solid. If we make a liquid out of it, what has that done to entropy? Well, it's given it more possible microstates, right? Because this solid has those molecules locked in place, right? They can't move. So they're limited to the number of microstates that you can propose for them. Theoretically, there's only one. But if you melt it, now these molecules can move all over the place. They have more microstates available. They're more random. So entropy has increased to go from here to here. And if you keep heating it, you will separate them and into, even if they have, well, in this case, we're saying that they have more volume with fewer molecules. Right? So we've increased the volume and we've made more possible microstates available. Right? So this positional probability has increased. And we get an increase in entropy as a process going from solid to liquid to gas. Okay. We can look at a system and its surroundings as a whole. What is the total randomness of the system and the surroundings during a process? Because we can move, depending on whether let's a little review here. System, surroundings, okay? And we isolate everything. So if we can exchange materials, mass between the two, and energy, that would be open, right? We can close the system, in which case no mass can change, can move. So no mass moving would be closed, but energy can move. Heat can move back and forth. Or we can isolate, in which case nothing gets into that system from the surroundings. And that's what we do very often when we describe a system and surroundings. We actually isolate both of them together. So nothing gets in and out here, but what goes on in here may simply be closed. Okay, those are the possibilities. I just wanted a little review. So, in an exothermic process, that implies that we increase the energy of randomness for the surroundings. Exothermic means heat's moving out, right? There's your Q, and it's going into the surroundings. That means the entropy over here is positive. It's increasing. Whereas endothermic, right? Everything is in terms of the system. Heat's moving in, and the entropy for the surroundings is negative. So what about the system? Well, in this case, entropy is negative. And in this case, change in entropy here is positive. Right? So we're making the surroundings colder and making the system hotter, which means entropy is increasing on the inside and decreasing on the outside. And for the other one, the exothermic, it's the other way around. So let's see if we can say something in general terms about these different scenarios. What's the sign of delta S for each of the following? Right? Increasing delta S is positive, decreasing is negative. Okay? So the evaporation of alcohol, it's going from a liquid to a gas. Entropy is increasing. Okay? I'll come back to that in a second. There, entropy is increasing. Freezing water, it's going from a liquid to a solid, so the entropy is decreasing. It's negative. Compress an ideal gas at constant temperature. You compress it, it's got less volume, but the same number of moles, your entropy is decreasing. Heat an ideal gas at constant pressure. Okay, if you heat it, the pressure is constant, then what's going to happen? Well, if the pressure is constant, you have to increase the volume, which means entropy will be positive, has to increase. And dissolve sodium chloride in water. This might take a second to think about. Okay, sodium chloride is a solid. Now we're going to put it into solution and separate the ions from that solid matrix. Entropy is increasing. Okay. Let me see what this statement about delta S cannot be measured directly. That's true. There's no way to measure entropy by any direct access. It has to be calculated value. And Boltzmann was another German, came up with this expression and various others that were derived from it for convenience, for experimental purposes. Then S could be calculated from whatever this constant is and the natural log of that function. I think that's work, but I'm not quite sure. In other words, the whole point of that inset is entropy must be calculated. Okay, that brings us to the second law of thermodynamics. The first law of thermodynamics says that for the whole universe, the change in energy is zero. The second law says that in any spontaneous process, there is always an increase in entropy. Now, for the universe, yes. And for isolated systems, the spontaneous process implies that entropy must be positive to be spontaneous. Okay. Now, when we say universe, we can also restrict the definition of universe. All you have to do is isolate the system and its surroundings from everything else, and that's your little universe. Okay, so there's a big universe and there's a little universe. Okay. This was the first law, right? The total energy of the universe is constant. But the second law says entropy is increasing. And here's another way of putting that. If we say delta S, we can say universe for the whole universe, or we can say, rather than that, we can say the total entropy for our system surroundings isolated is then equal to the entropy of the system plus the entropy of the surroundings. Okay, that's the way I like to look at it because it's more practical. This value is total based upon what you define as your operating universe. And there it is. Okay. So I'm going to hammer this one again. With this expression, if that value is positive, then the process is spontaneous. If that value is negative, then it's non-spontaneous. Okay? Get out of the way so we can see it. There's another case we haven't looked at yet. What if delta S is 0? We add these together, and maybe one of them is negative and one of them is positive, but they're equal in magnitude. They cancel each other out, and this is 0. So if delta S is 0, we're at equilibrium. Okay. Now, we talked about positional randomness, and that's where we started our argument, where we have the gas moving from one bulb into an evacuated bulb. That's positional randomness, because there are a whole lot of different positions that those molecules can occupy, lots of different microstates. But we can also look at entropy in terms of energy randomness. So in this example, where we have a liquid going to a solid, that involves an liquid to a solid is exothermic. As it goes from liquid to solid, it has to give up energy because those molecules now are slowing down, right? And we can't create energy, we can't destroy energy, it's got to do something. So it gives up the energy from the system into the surroundings. So when that exothermic process occurs, then energy randomness favors the formation of the solid. Yeah. We're looking at this in terms of energy now. We're not saying anything about entropy yet. But what we are saying is that with that energy leaving the system, the energy randomness favors the formation of the solid. But positional randomness favors the liquid, right? Because there are more microstates. So there's kind of a tug of war between energy randomness and positional randomness. And the positional randomness decreases from liquid to solid. That reduces the number of microstates, and that's unfavorable in terms of entropy. So we have to look at the balance between the two. What's the balance between energy randomness and positional randomness? Which one wins? That's a good question. Which takes precedence? So under what conditions does the system favor one over the other? As temperature increases, positional randomness dominates. Okay, now let's look at it in terms of let me see, do I have that on the slide yet? I don't want to steal my own thunder. No, I don't. Okay, so I'm going to use this analogy. Suppose you have two people. Right? This guy is a millionaire. Millionaire. And this guy is average Joe. Right? He's just barely getting by. If I, as a third person, want to give this guy $10, right? What effect does it have on his overall wealth? Almost nothing. Whereas it may be of more value to this guy, $10. Let's say $100. Well, it's $1,000. $1,000 to him means nothing. He's already got $1 million. $1,000 to this guy means a lot. So think of that in terms of if the temperature is high, what influence does energy have on the outcome? He's already got a lot of energy. If we add a little bit more energy, on a percentage basis, it makes no difference. So in this case, the dominant process is positional randomness. That's what makes the difference. Whereas with this guy, this added wealth or energy makes all the difference. So if he's already at low energy, then energy randomness is preferred to positional randomness. I hope that makes sense. So in terms of chemistry, as the temperature increases, positional randomness becomes the more dominant process. So at high temperature, we're looking at positional randomness to tell us whether the process is spontaneous. Okay, as temperature decreases, then energy randomness is favored over positional randomness. So at what temperature is there a balance between energy randomness and positional randomness? Where do they cross? Right here, at equilibrium. So for a solid turning to a liquid, that equilibrium is at the melting point, where the phase change occurs, where you have solid and liquid together. That's the crossover point between positional randomness and energy randomness. So let's look at other possible changes here and see if we can use the concept of positional energy and positional randomness to some processes and imply whether they're spontaneous, non-spontaneous, or we just don't know. That's a possibility. Maybe we don't have enough information. We can't tell. Okay. So a reaction that's exothermic and becomes more positionally random. If it's exothermic, it's losing energy, theoretically decreasing in temperature. So now positional randomness is preferred. So more positionally random, that is a spontaneous situation. Both driving forces are favorable. Right? Exothermic implies a favorable reaction, and positional randomness is also favorable. So this would be spontaneous. What if it's exothermic, but it becomes less positionally random? Can't tell, right? Because it's a balance between the two. Which one wins? We don't know. Exothermic is favorable, but position is not. So which one is the greater? It will depend on the temperature. If it's high temperature, then the exothermic becomes, a loss of energy becomes less important, and the positional becomes more important. So in that case, then positionally less random means that it's not spontaneous if the temperature is increasing. How about endothermic? Energy is being added to the system, which is energy randomness is being endothermic, and becomes more positionally random. Here again, we have a balance. Endothermic is not favorable, whereas positional is. So there, again, it would be a balance between the two. Which one is favored? Whereas endothermic and less positionally random, now both of them are unfavorable, and that means it would be non-spontaneous. We can make a conclusion, draw a conclusion about this one and that one, but these two are inconclusive. And this statement is true. One thing that's true about both of them is A and D are not affected by temperature because they're both favorable. Whereas B and C are influenced by temperature. High temperature means that energy randomness is less effective. Low temperature means energy randomness is more influential than positional randomness. Okay. So delta S of surroundings. Now we're going to talk about system surroundings, and we're going to break it apart and look at just the randomness of each of the components. What's the delta S of the surroundings? Okay. We looked at that earlier when we looked at exothermic reaction, right? Exothermic reaction means that the surroundings are becoming more random. We're adding energy to it. And so as heat leaves the system and goes into the surroundings, the randomness in the surroundings increases. So exothermic, which is delta H minus, right? Remember, exothermic is always in relationship to the system. This transfer, this heat estimate is negative because heat is leaving the system. But it's also increasing the delta S for the surroundings. So that should be a positive value. If heat is entering the system, randomness in the surroundings is decreasing. That's an endothermic process, which has a positive sign. The magnitude of delta S of the surroundings depends on the temperature. What is the temperature? That is active at the time of this transfer. So the change in entropy has a greater effect on the surroundings when it starts at a lower entropy than if it starts at a greater entropy. In other words, the value of delta S. Let me back up and look at this again. If we start at low entropy in the surroundings, then the change is a greater, like our example with the millionaire and the average Joe. If we start at large entropy, then any change in entropy is on a percentage base much more influential than if we start at low entropy. So at low entropy, the change is more effective, more influential than if we start at high entropy. So in other words, what we're saying is the delta S for the surroundings is directly proportional, and that's what that means, directly proportional to the heat transferred. It's directly proportional to Q, right? So the more heat transferred, the greater the change, but it's inversely proportional to temperature. Okay, so if the temperature is greater, then the change in entropy is going to be less. So this relationship, delta S surroundings, is Q divided by T. But we have to account for the sign, right? Because we're looking in terms of the system to put a sign on the Q. So that's why heat, let's see. Oops, I went too far. Hold on a second. Here we go. Heat is in terms of joules. Temperature is in terms of Kelvin. And this is the magnitude of the energy change. That's the driving force. What's driving the reaction? And if we put a sign on it for exothermic processes, we should have a exothermic. The surroundings are going to increase in entropy, so the sign should be positive. And if it's endothermic, energy is being drawn out of the surroundings into the system, so the delta S for the surroundings is going to be negative. So here's the end result of all of that. We're actually going to use, instead of Q, we're going to use not the actual movement of heat, but we're going to use the potential, the enthalpy. So we're going to change this to an equivalence. And that's for the surroundings. The entropy is equal to whatever the enthalpy is, divided by the temperature, take the negative of it. Okay. I mentioned this earlier without explaining it. Delta H is enthalpy, and Q is heat, actual heat movement. So there is a difference. They're not the same thing. They're related, but they're not the same. Delta H enthalpy, Q heat, they're different values. But that makes it difficult on chemists because we measure heat, but we want to know enthalpy. All right, so maybe there's a time when the measured amount of heat transfer is equal to the enthalpy. Is there a time when we can say they're both equal? Right? If they are, that's great because we can measure this one, and this one is calculated. So before we move on, enthalpy is a thermodynamic potential for a reaction. Kind of like internal energy, but not exactly right. They're related. And enthalpy is defined by this equation. Right? Enthalpy is actually equal to the internal energy change in the system plus a change in pressure times volume. So pressure times volume, whatever that change is, must be added to internal energy to give you enthalpy. Okay? So, but what is delta E equal to? Remember, we saw that in thermochemistry. Delta E is equal to Q plus W, heat plus work. Right? So we substitute that in here. Okay? Now, what if the process takes place at constant temperature? Constant pressure. That means this factor, this P, doesn't change. That means we can pull it outside, and now only the volume changes. The P is constant, the volume is allowed to change. Okay, so here we've done that. We just pull this P outside. It's constant now. Doesn't change during the process. Okay. This is another equivalence that we ran across in thermochemistry. where work is equal to minus P times delta V. That was first semester. So I'm just dredging up these old formulas for you. Work is equal to the negative of pressure times a change in volume. Right? And we did that whole derivation in a previous chapter. I think it was, in my textbook, I believe it was chapter 6. So if we substitute this in for the W, then we get enthalpy equals Q minus P times V for the W plus P times V. They cancel one another out. So under those conditions, enthalpy and Q, or heat transfer, are equal. So what do you have to do if you're going to run an experiment and you want to infer enthalpy from your experiment? You're going to measure this value. So you have to be certain that pressure does not change during that reaction. If pressure is constant, then you can say that your measured Q is equal to the enthalpy. All right. So now that we've defined something about the surroundings already. How does the delta S and how does system, surroundings, and total, I prefer total here, how do they interplay? Well, we know that this one, the total, is equal to that one plus that one. Right? Those two, system and surroundings, added together to total. So let's look at it. Right? If delta S is positive, system is positive, and surroundings is positive, then this one has to be positive. Here we go. Then the summation is positive and the process is spontaneous. If I keep going the wrong direction. If delta S for the system, if entropy in the system is decreasing and entropy in the surroundings is decreasing, and that can happen both at the same time, then when you add those together, that reaction will not occur in the forward direction as written. So what we're saying is that that process is not spontaneous as written. But in the opposite direction, it is spontaneous, because if you go backwards, then this becomes positive, that becomes positive, and that's positive now. If the enthalpy, the entropy for the system is increasing and the entropy for the surroundings is decreasing, then it depends on which one is bigger. Right? If delta S has a larger magnitude than if the system is larger than the surroundings, it's spontaneous. The other way around, if the system is negative and the surroundings is positive, then the surroundings would have to be larger than the system in order to be spontaneous. All right. Now, our discussion up to this point has been instructive in terms of determining spontaneity of the reaction related to entropy. But it's not very useful. We want things to be more practical. I'm getting a horrible glare on that screen. I hope I can filter that out in post-processing. So it falls to Josiah Gibbs to make sense and make a more practical application of what we know so far. And what Gibbs was interested in was All right, if you've got a spontaneous process, you want to know how much of the energy that comes from that process is available to actually do work. Otherwise, what's the point? I mean, it's just academic. If you let a reaction go spontaneously and you don't extract any work from it, then why bother? Well, some chemists, they do it just for fun. But Gibbs wanted to know how much of that energy is available to do work. So, to make a long story short, this is Gibbs' equation. And the delta G is called free energy. And that means that this is the energy that's available to do work. This is the enthalpy of the system. And of all of this enthalpy, energy that's available, total energy that's available, well, not total, it's the enthalpy energy that's available. If you subtract what's lost to entropy, then you can find out what the free energy is. So what we're saying is, in this equation, is that the Gibbs free energy is equal to enthalpy minus the temperature times entropy. And the temperature is held constant, right? Notice it has no delta in front of it. So the temperature is constant. If there is no subscript in any of these symbols, then we're implying system. If we're interested in surroundings, we're going to say it's surroundings. Otherwise, we're saying it's system. So all of this is system. So the delta S for the system times the temperature subtracted from the delta H for the system is the Gibbs free energy. Okay. This is another way of expressing it. You can write it this way. All we've done is divide the whole thing through by temperature. So divide through by temperature cancels out. Now you've got temperature here, you got temperature there. We're also going to divide through by negative temperature. So that makes this one positive. That's all that's happened. It's just an algebraic manipulation. And the reason we did that is because we know this relationship. Delta S for surroundings is equal to negative enthalpy divided by T. So now that we have this value right here, then we can substitute delta S for surroundings there. Okay? So that's what we've done. We said we put delta S for surroundings. This is delta S for the system. And this is equal to negative delta G over T. Based on that, derived from this to here to here. And we also know that surroundings plus system and entropy is equal to total. Right? Okay. So if this total is spontaneous when it's positive, that means this expression must also be positive. Okay? And T is always positive because it's Kelvin. So what does that mean? That means if this is positive and that negative sign is out here, that means that delta G, when delta G is negative, then delta S total is positive. And if delta G is negative, we have a spontaneous reaction. That's the whole point of this manipulation. Okay, this out of the way. So there it is again. The total entropy is equal to the negative free energy change divided by T. As long as the free energy is decreasing, as it's negative, change in free energy is negative, then the reaction will be spontaneous at constant temperature and pressure. So negative delta G means spontaneous, just like positive delta S means spontaneous. Okay, let's see if we can make sense of that now. A liquid is vaporized at its boiling point, constant pressure. So what's the sign of each one of these? Is any work being done? Well, let's see, at constant pressure. Oh, if it's at constant pressure, then as the liquid is vaporized, it makes gas, you have to increase the volume. Okay, so work is being done on the surroundings. As we vaporize that liquid and make vapor up here, then that piston under constant pressure has to go up. Okay, so that means that we are doing work on the surroundings. And this is the system. That's why W is negative. Okay, how about Q? Well, Q is in terms of energy being added to, heat is being added to the system. In order to vaporize this, we have to put Q into the system. So it's positive. Okay, there you go. You have to add heat in order for this to happen. How about delta H? Well, the constant pressure means that Q and delta H are equal. So they're both positive. Okay. How about the delta S for the system? Okay, here's the system. The system should be positive also. We're increasing randomness. The gas is more disordered. As a gas, it's more disordered than it is as a liquid. How about the surroundings? Right? You're losing energy from the surroundings. Delta S for the surroundings should be negative. Oops, let me get this out of the way. There we go. The surroundings become more ordered in terms of either randomness or energy, either way that you look at it. You should get more ordered in the surroundings. So what is delta G? Delta G, we're at the boiling point. Delta G is 0. How do we know that? Because it's at equilibrium. Any system at equilibrium has no free energy to offer. Yes, that's true. At equilibrium, there is no free energy. Only when you're outside equilibrium can you extract energy from the system. So the enthalpy of vaporization of a substance is 45.7 kilojoules per mole. And its normal boiling point is 72.5 degrees Celsius. Let's calculate the system entropy, the surroundings, entropy, and the delta G for the vaporization of 1 mole of this substance at 72 degrees and 1 atmosphere. Okay? If it's at the boiling point, we're now at the boiling point, then delta G has to be equal to 0. There's no other possibility. It's at equilibrium as long as it's boiling. The surroundings, we came up with a surroundings formula. It's negative enthalpy divided by temperature. So we take the enthalpy, and kilojoules has to be converted to joules. So that's why we have 10 to the third here. The negative sign divided by Kelvin temperature. Okay? So that's minus 132 joules per K mole. Joules per K mole. There's a division right here. Okay, so that's the surroundings. And we got delta G is 0, got surroundings. How about the system? Well, at equilibrium, the delta S for total has to be 0. So if we know this one is surroundings, then this one has to be the same magnitude but opposite sign. So there you go. There's your answer. All right. So at the boiling point, at the melting point, the systems are at equilibrium and delta G is 0. That's our starting point.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of 0, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash nonpolar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long nonpolar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the nonpolar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale, but the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, so this this table summarizes what Professor Dave just discussed. If we want to understand or predict spontaneity using the Gibbs free energy equation, we look at the balance between enthalpy, temperature, and entropy. And if the entropy for the system is positive and the enthalpy is negative, then this sum will always be negative, which means it's spontaneous. That's your first option. If the other way around, if you have a negative delta S and a delta H that's positive, then this summation will always be positive, and that's not spontaneous in the forward direction. But in the reverse direction, it will be spontaneous. The other possibility is where both values are negative or both values are positive. If they're both negative, then this negative will be a positive value and this will be a negative value. And then it depends on which one is bigger, right? So if this one is negative and this one's positive, if both of them are positive, pardon me, if both of them are positive, then this will be positive and this will be negative. But this one will win only if T is very high, because it makes this term bigger. Very large, that gives you a negative delta G. So this one, where both are positive, is only spontaneous at high temperature, where exothermicity is unimportant. Right? And the let's see. Yeah. Now, if they're both negative, then this becomes positive, and this is negative. And then under those circumstances, we want to minimize this one by making a small temperature. So at low temperatures, both are negative. That would be more likely to be spontaneous, because this is negative and that one is a very small positive. All right. So let's see. Gas A reacts with gas B to form gas AB at constant temperature and pressure. So gas A reacts with gas B to make AB. Okay, at constant temperature and pressure. The bond energy of AB is much greater than that of either reactant. So the bond energy holding these together is less than the bond energy that holds these two together. Okay, there's a balance there. Predict the sign of each one. If the bond energy here is greater than there, that means it's more stable and it has given up energy. So this is exothermic. Another way to look at that is this. Okay? Reactants here, like that. This is AB, and this is AA and BB. That's an exothermic process. Oh, we can also look at it this way. Remember how we calculated the enthalpies based on bonds broken minus bonds formed? Okay, so that's exothermic. Right? That's one way to look at it. This is another way to look at it. So that means that delta H, the enthalpy, is negative. It has to be. Our sign convention says exothermic is negative. Well, how about the others? Well, if we know this is negative, then that makes this whole value positive, and this one should be positive. Right? The enthalpy of the surroundings should be positive. How about the enthalpy of the system? We have to assume that the enthalpy of the system is in the neighborhood of zero. Excuse me, the entropy of the system is in the neighborhood of zero. We don't know for sure. We could say that because there's 1 mole of this and 1 mole of that, 2 moles of that, that the number of moles says that they're equal on both sides. You got 2 here and 2 there. So we're saying that the entropy of the system is about 0. How about the total? Well, if you add those 2 together, you get a positive value, don't you? Okay. So I guess that's all we're going to do with that one. The third law of thermodynamics was mentioned by Professor Dave, and it just says that a perfect crystal at 0 K, absolute 0, has 0 entropy. That's what this statement says. So the entropy of a substance always increases with temperature. So if we're going to do any calculations, it would be helpful to have tables that provide standard entropies for any changes that we're interested in, or any standard entropies for any substance, element, compound, whatever the case may be. And since the temperature is going from 0, where entropy is 0, then the entropy should always be positive. The standard entropy should always be positive. So the entropy of a reaction, then, we sum the entropies of the products and subtract the entropies of the reactants. Here we have a reaction of sodium and water to make sodium hydroxide and hydrogen gas. Now remember that the enthalpy, the delta H of some things is 0. The entropy of this one, sodium in its standard state, is 0. And this one, this element in its standard state is 0. If we were doing enthalpy. But for entropy, every term has a value. So the standard entropy for sodium is 51. Water is 70. And the state matters. Solid, liquid, aqueous, sodium hydroxide is 50. And hydrogen gas is 131. So we would take 2 times this one, plus one of these, and then subtract 2 times that one, and 2 times that one. And we end up with a negative 11 joules per K. So that's the standard entropy for this reaction. Standard free energy change. We're still working at, for standard conditions, 1 atmosphere pressure, 25 degrees Celsius, which will be 298 K. And if there's a concentration involved, like an aqueous solution in our previous example, it would have to be at 1 molar concentration. Those are standard conditions. So what's the change in free energy that will occur if the reactants in their standard states are converted to products? Well, we need to know each one of these values. So the delta G for the reaction equals products minus reactants. Right? Oh, it's not going to tell us. It just says that we can calculate it here, and then we can relate it to any other factors there. And that's the whole point of this one. So what if we had set up a condition where a diatomic molecule spontaneously forms its atoms? So this one goes to this one. Okay? What's the sign of delta H? Standard conditions: enthalpy, entropy, and Gibbs free energy. delta H would be, oh, we're just going to give you the answers. We need to explain it, don't we? So delta H, standard enthalpy, would be negative. It would lose energy. The system would lose energy. As we go from this one, the bond is breaking, which means we have to put energy into it. Now that doesn't make any sense. If it's going from a diatomic molecule to its atoms, the bond is breaking. Seems like delta H would be endothermic. Is there an explanation? Oh, I see. We're starting with delta G. If it's spontaneous, it has to be negative. Delta S standard, because two atoms is, oh, I'm going the wrong direction. That's why it didn't make sense to me. There, okay, now it makes sense. Right, we've still got a negative delta G because it's spontaneous. But if we're going from two atoms to one molecule, we're decreasing the entropy. We're going from 2 to 1. And that is more ordered. So a delta S for this system would be negative. How about delta H? Well, when these molecules come together, they give off energy, right? Because they're more stable as a unit than they are as separate atoms. So delta H would be exothermic. That makes it negative. Okay, so now it makes sense. Okay, what about this situation? PCl3 gas plus chlorine gas yields PCl5. And the delta G is given as minus 92.5 kilojoules. First thing you notice is the way it's written, under standard conditions, this is spontaneous. That's what that means. It's spontaneous under standard conditions. If we change the conditions, then it may not be spontaneous. You always have to keep that in the back of your mind. What will happen to the ratio of partial pressures of PCl5 to PCl3 if the temperature is raised? Okay, if the temperature is raised, now we have actual delta G that we're looking for. Well, actually, that doesn't answer the question. We're actually looking for the ratio of this to that partial pressures. All right. The ratio will decrease if the temperature is raised. Okay, if we increase the temperature, now it's not at standard temperature anymore. If we increase the temperature, we're going from 1, 2 to 1. So if this is less than 0, this is a negative number because we're going from 2 to 1. And we increase the temperature, it becomes more negative. No, it becomes more positive, excuse me. Increase the temperature, this is negative, increase the temperature, becomes more positive. So this gradually trends toward, not the standard conditions, but the actual delta G trends toward less and less spontaneous, which means if it's less and less spontaneous, then the ratio of PCl5 to PCl3 is going to decrease because now we're producing less and less of this relative to that. The reaction is less spontaneous, so the equilibrium tends to go back the other direction. So that's why the ratio decreases. We're decreasing the amount of this because this is becoming more positive. I hope that makes sense. Let's see, delta S is negative, unfavorable. Yes, because we're going from 2 to 1. Yet the reaction is spontaneous under standard conditions. Delta H must be negative or favorable. Right? If this is negative, then this one also has to be negative. Yes. So as the temperature is increased, the reaction proceeds to the left. Okay, we're using, it's exothermic. Okay, we've inferred that the heat is being produced as a product. Right, so that's another way of explaining this. If now that we know that this is on the product side, if we increase the temperature, we're driving the reaction backwards. Okay? So either explanation arrives at the same conclusion. Okay. So what we really want to know is not is the reaction spontaneous under standard conditions. I mean, that's a starting point. But what we really want to know is the reaction spontaneous under conditions that we choose? So the relationship between standard conditions and actual delta G for our chosen conditions has the delta G standard conditions, plus we have to introduce this term, right? Pressure and temperature and the ideal gas constant. Now this ideal gas constant is not the one with atmospheres in it. This is the one with joules in it. 8.315 joules per K mole. That's the one you use for this one. Okay. This is for a gas situation. This is for solution situation, where you calculate the Q for your reaction. So you have to know what are the beginning conditions, and we know how to calculate Q. And all you need to know is what's the standard one, and then what is the R, and what's the temperature, and then calculate the Q, and then we can determine what the delta G is. Because if this is not Q, if it's at equilibrium and that's K, then we don't get a free energy out of it. At equilibrium, the free energy is 0. Okay. So for, let's see. What does delta G mean for a chemical reaction? Well, first we have to discuss delta G in terms of phase change. So a phase change is like a ball rolling down from A to B. There's no interruption in the process. It just goes there. It goes to completion, in other words. Whereas for a chemical reaction, as an example, we don't go to completion. We go to an equilibrium, right? We go to a lower energy profile for stability. That's where the reaction wants to go. So at equilibrium, the actual delta G is equal to 0. But under standard conditions, it usually is some other value, either positive or negative. But at equilibrium, delta G is 0. So at equilibrium, we can take that former equation and say, okay, now we know that delta G is equal to the standard delta G plus this term, but now instead of Q, we put K in there because that's equilibrium. Okay? So if we solve that, this is 0, we solve it for delta G, then delta G is minus RT log K. What does that mean? That means that if you know what delta G 0 is, you can calculate K at this temperature. Or if you know what K is and you know your temperature, you can calculate the standard delta G. So if we have a process where we're going from this gas to that gas, we can express the free energy for each gas in terms of its pressure. The natural log of the pressure of A here and the natural log pressure of B is there. The total G, for going backwards and forwards, the total G then is the sum of these two. So if we have G, if we have A reacting to B, it gradually decreases. Right? Gradually decreases. And the equilibrium occurs in the middle. So if it's coming from this direction, it's going down that way. If it's coming from this direction, it's going that way. So it depends. Is it going this way or is it going backwards? So the fraction of A that's reacted meets in the middle. And at this point, we have an equilibrium. The equilibrium point occurs at the lowest value of free energy. And the lowest value of free energy is 0. Okay. Wait a minute, I'm going backwards. Sorry. Here we go. As A disappears in this one or in this one, the free energy decreases. Since P is also decreasing, the partial pressure of A is decreasing, so our calculation, that's on the previous one. Here, our calculation, if this is decreasing, then G is also decreasing, becoming smaller. It's trending towards 0. And the G for B is increasing because we're making B as A disappears. And as long as the free energy of B is less than the free energy of A, the reaction will proceed as written from left to right. When the free energy of B is equal to the free energy of A, then the total, then the total G being equal to the G of A and the G of B, the free energy of each one added together, and the change is equal to the G of products minus the G of reactants, that has to be equal to 0. Right? So one of these has to be trending toward, well, decreasing, the other one's increasing, but eventually the magnitudes equal and the signs are opposite and they cancel out and become 0. That's where you reach equilibrium. Okay. So we can say something about the free energy and about K, their relationship, simply because this is the relationship between standard free energy and K. So if delta G0 is equal to 0, then K has to be equal to 1. Right? Why? Because the natural log of K is equal to some value. And if this is E, right? then where is delta G equal to 0? Right, you've got R and T out here, right? Well, where is that equal to 0? Where is delta G equal to 0? It's when this value is equal to 0. And that means K has to be equal to 1. Why? Because what's the power of E that makes K 1? Right? E to the 0 power equals 1. Right? It's the logarithmic function. So that only occurs when K is equal to 1. So if K is equal to 1, then delta G is 0 and you're at equilibrium. What if delta G is less than 0? Then it's spontaneous. And if delta G is less than 0, right, negative, negative, then this one must be greater than 1. K has to be greater than 1 in order for delta G 0 to be less than 0, to be spontaneous. If it's not spontaneous, then K is less than 1. So we can infer from K that if you're going from reactants to products, if the products are favored, then it should be spontaneous if K is bigger than 1. But if K is less than 1, then the reactants are favored and it's not spontaneous. Okay. So what is the maximum possible useful work obtained from a process at constant temperature and pressure? That's equal to the change in free energy. Right? So here it is, change in free energy. That's the maximum amount of work that can be obtained. Now, the maximum amount of work can only be obtained from reversible processes. In other words, what that means is the change has to be infinitesimally small. If you get bigger than that, then you lose. You don't get your maximum work out. Right? So this is a theoretical situation. But we got to start somewhere. Since all real processes are irreversible, then the maximum work can never be reached. You always lose something in the process. So what's the temperature dependence of K? The equilibrium point occurs at the lowest value of free energy available to the reaction system. So since this actual free energy is equal to 0 at equilibrium, and it's equal to this term, then we can solve for delta G equals this one. Okay? And we can say at equilibrium, then this delta G is minus RT log K. Okay, we know that. But that's also, delta G is also equal to the enthalpy minus T entropy. So if we divide the equation by minus RT, what is that going to do? It's going to get rid of RT out of here. Right? That's what that does. So here we've got, well, we've skipped a step. Let's do it over here. Delta G0 equals minus RT log K. That's equal to delta H0 minus T delta S0. Okay. Now we're going to divide the whole thing through by minus RT, minus RT, minus RT. That's an equal sign there. So this one cancels out right there. So log K is now sitting by itself. Okay. So here it is, log K sitting by itself. And that log K now is equal to delta G0 over minus RT. It's also equal to let's see. Okay. We're not interested in this one right now. We're interested in this part over here, which is delta H 0 over minus RT and plus T delta S 0 over RT, and the T's cancel. Okay, so we end up with log K equals minus enthalpy over R, and then we pulled out this T, right, times 1 over T. Right, so this is in the denominator. We just pulled it out here. And this part is right here. And then this part stays unchanged. Okay, so now, what does that look like? Look to me like a straight line. Y equals mx plus b. Y-intercept, slope of the line. This is x, this is y. So if we plot, say we've conducted an experiment with a single reaction over different temperature ranges. So we got the several Ks are measured at different temperatures. And we plot the inverse of the temperature against the log of those Ks. And we get this straight line. And here's the expression. So if you see this straight line value, we know that the Y is equal to log K. And we know that the X is equal to 1 over T. And then this minus 11645 is equal to this minus enthalpy over R. So you can calculate the enthalpy of the reaction if you plot it like this. You can also take this value and set it equal to this expression and find out what the standard entropy, entropy. Find out what the standard entropy is from this term. Find out what the enthalpy is from that term. That was the whole point of this manipulation, just to show you that how to get this information from an experiment and a graph of that experiment. Okay, achieving the maximum work available from a spontaneous process can occur only through a hypothetical pathway. That is a reversible pathway, which, like we said, never happens. That is a theoretical impossibility. Any real pathway wastes energy. Real processes are irreversible. Okay, so here's what it looks like in terms of thermodynamics laws. The first law says you can't win. Right? You can only break even. You can't get more energy out of the system than you put in. That's what we mean by you can't win. Second law says you can't even break even. There's no way to break even, because any transfer of energy will result in a waste of that energy, unless the process is coupled to absolute zero, and that never happens. And the third law says you can't get out of the game either, because you cannot achieve absolute zero. You never get that perfect crystal with S equals 0, because you can never reach absolute zero. Why? Just think about it. How do you make things cold? How do you go toward absolute zero? Right? You get colder and colder by transferring heat from one process to another, makes this one colder. So if you transfer from this one to this one, then this one will decrease in temperature, right? If you're headed for absolute zero, how are you going to couple this one to a lower temperature so that you can make absolute zero? It won't happen. There's nothing lower than absolute zero, so you're never going to get there. All right. So the moral of the story is when you use energy to do work, ostensibly, you always degrade its usefulness. In other words, when I use energy from coal to make something else, then the products are less useful. And in fact, if you burn any hydrocarbon in oxygen and you make carbon dioxide and water, then you're essentially at ground zero. I mean, you can't go any further than that. Okay.